So thank you all for coming. I think we've got over 40 of us here this evening. So thank you for coming out and joining us. And thank you for Jim, who's kindly agreed to for this session to provide an overview of engine management for the pilot, the piston engine. For those who don't know Jim, which can't be many people, he heads up the marketing and membership working group in PPL Europe, and he's been a member since 2008. So what's that now? 14 years. So Jim, you okay to share? Over to you.
I need to set up a pointer. There we go.
Please put up questions throughout, either direct to Jim or to myself, and we'll see those in at the right time and answer them.
All right, everybody. Okay, good. So thanks, Craig, for the introduction. And sorry, I've just realized that something is blocking my view. Right. Before we start, I'd just like to say a few more words about me to give you some my credentials for making this presentation. I'm a pilot of nearly 2,000 hours, and I learned to fly when I was 18 in this Chipmunk. It was a university air squadron, and that's me flying over Southport Beach rather a long time ago. Anyway, then I had a break after I left university and bring up a family, had no money, and then when eventually family left home, some money started to reappear, and I purchased this Cessna 182, from which I used that airplane to get my instrument rating, and joined PPL IR about 15 years ago. And I used this airplane to go on lots of trips in the early days, and learned a huge amount as a result of being part of PPL IR, and felt that once they'd given me so much, I thought it was a good idea that I should try and give something back. I then sold that airplane and bought this airplane because I needed an autopilot. That 182 didn't have an autopilot, so I bought this TB20. And I've been on a lot of PPLR trips with that, many of them with Eleonora, who's on the call today. Since then, I bought a number of different aircraft, some of them with Graham, who's on the call, Graham Mountford. This 180, this 210, Graham and I share. Now, he originally bought it and I bought a share in. It's presently sitting in the hangar at Turweston without any wings, and because it failed its wing spar AD, but hopefully we'll be back in the air. This Archer was bought for the flying school that I'm helping to run. And this Arrow 4, Turbo Arrow 4, was also bought with Graham, and we still own other aircraft. For the last 5 years or so, I've been also running Cranfield Flying School, and that together with my own aircraft, I've built up quite a bit of experience in a large number of maintenance issues, particularly with respect to engines. I built one engine on the TB20 from the ground up, and have installed a number of zero-timed overhauled engines, one in the 182 and the Archer down here, and many others in the school aircraft. So I've done quite a few overhaul installs. And I've also done 20 break-in flights for newly overhauled engines. But I must emphasize that I'm not an engineer. In fact, I'm trained as a scientist. I'm an organic chemist by training. But I hope the experience that I've accumulated over the years as a pilot and working with lots of different engineers will be of interest and of use to others, and that's what I'm intending to present today. To help me out, though, if we get questions above my pay grade, I've press ganged Rob Ronaldson and two of my friends, Rob Ronaldson and Graham Mountford, to help. Rob, amongst other achievements, set up Gamma Engineering in Oxford, to engine overhauls, but he's also done hundreds of other things which we haven't got time to go into, but he's my go-to man for anything to do with engines when I get out of my depth. Graham Mountford runs Aki Engineering at Turweston, and he wants me to point out that he's also not an engineer, and in fact originally another organic chemist, which is probably why we get on so well. Anyone who knows anything about engines, though, will know that it's not hard science. Every engine is individual. Just like people, we start off roughly the same, but we get molded by our experience in life. And this results in a lot of different opinions about how to run them and how to maintain them. And that includes me. So take that in the spirit I intended. A lot of this stuff is, it's personal opinion from me, but based on hopefully a lot of experience. I intend to present a lot of material actually, and it takes a bit of digesting if you're new to it. And we don't have a lot of time to go into the depth. But if there's interest, we can do another seminar on different aspects of what I present. I hope I haven't bitten off more than I can chew either, but if we run out of time, I can drop the last session and we can run another session on it. So there will be short breaks for discussion and questions after each segment, and there'll be 4 short polls interspersed throughout the presentation, and then we can ask questions as we go through. To start with then, let's see who's actually attending, and I'm going to use this to build up some data about our own experiences here. Now, Craig, can you do that? Oh, because I can't see where are we?
If it lets me get off mute, yeah, I'll launch it now.
Can you launch it?
The first poll is there. Hopefully you're all seeing that. They're all coming in. We've had 39 of the 45, 40, 41. Last few, 42 of 46.
Okay, so we've got a fair spread of different experience levels. By the way, I should have said in advance, this has got to be piston engine hours. So any of those jet jockeys out there who built up 20,000 hours on 737s, that doesn't count. I'm only talking GA hours, yeah. All right. A bit late to say it now.
Show the results of the poll.
Yes,
please. We can't see it yet.
Yeah, we'll end the poll, and the results coming up there. Colin, can you see them? Cool. So yeah.
Everybody see them?
Yeah, can you see them, Jim?
Yeah, I can see them. They're good. Yeah.
Okay.
Okay, so we stop sharing that, presumably, do we?
Yeah, if you're happy with it, I'll stop.
Okay.
There you go. Brilliant.
Right, so we're going to use those hours later on for some calculations. Okay, so let's get on with it. So once I'd obtained my instrument rating and become familiar with the logistics of long distance flight planning and execution, I found, which has become a lot easier over the years with the modern tools for flight planning, I found that when it came to planning a long journey in my aeroplane, I spent most of the time worrying about 2 things. The first thing was the weather, which we're not going to talk about today, but secondly, the engine. When we're a long way from home, we don't want anything to go wrong with the engine. And there's some basic rules here when it comes to engines. The primary rule, which I learned very early on, is that when you're over water, the engine always runs rough. We all know that phenomenon. When you only have one of them, you don't want it to fail, particularly over water or hostile territory. But at the same time, you want to get as much distance out of the very expensive fuel you've just purchased, amongst other things. And that latter point has become doubly or even trebly relevant today as Vladimir Putin continues to wreak havoc with the world economy. So what I intend to talk about then is how we as pilots should go about managing the engine side of flying, and mostly single engine aircraft on long distances. And that's what we're mainly trying to do here. And I've split it into 4 parts. The first part is, what's the problem? Do I really need to worry about the engine? The second part is a description of some of the more common problems that occur with engines. The third part is some day-to-day observations about how we should manage and reduce the risks of engine failure when we're flying. And finally, a section on advanced engine management, which is mostly about running lean of peak. Now, whether we can get to that last section, I'm not sure, but we'll give it a go. So firstly, what's the problem? do I really need to worry? And here's some statistics. So we're talking about aircraft accidents, and here is a visual description of the number of accidents, and now some health warning. This is from the US. This is data from the US. I don't really think there's any reason why it should be any different from UK data. Oh, sorry, European data. But I can't get hold of the European data. But they're the same engines and the same aeroplanes and roughly the same pilots. The numbers are estimates. The NTSB in the US acknowledged they have really no idea how many hours have actually flown in the US, and I'm sure the same is true in Europe. Secondly, the data comes from accident reports, and it doesn't include any data that's not reported. So, and many engine failures, particularly where there are no injuries, and even when there's been when there's been damage to the airplane but no injuries, they don't get reported. So you get a lot of engine failures that don't get into this into the statistics. Prop strikes are a pretty good example, but this is the data we have to work with. So it's as good as anything. So you can see the large majority of accidents are actually loss of control, probably going inadvertently into cloud. And then the second block is controlled flight into terrain, CFIT. Also probably as a result of going into IMC. And this chart is as good an advert as I can find of encouraging people to get their instrument rating. But that's not for today. Then we get engine failures, and it's a smaller amount. And then the white dot is actually the fatalities that come from engine failure accidents. So it's a relatively small amount, and we'll come back to it. We'll look at some real data now. So here are the trends, and it's on per 100,000 hour basis in the US. You can see the trend has been coming down somewhat. The actual fatalities, which are just about 1 per 100,000 hours in total, is relatively low. So you could basically say to start with, the risk of dying from an airplane is low. It's about the same as the risk of getting into a car, a bit more, but not a huge amount more. Now we go on to the actual what happened. Forgetting about the other forms of accidents, we're now looking at the mechanical accidents, which is what we're more interested in. And these are actual numbers done on a yearly basis, and this comes from the MAL report in 2018, run by AOPA in the US. And you can see the number of fatalities down here. So the number of mechanical accidents is about 15% of the total, and 1% of the fatalities are from mechanical accidents. So it's a small number, but still not rare. What happens if the engine quits? Well, that's what happens when the engine quits. None of these were fatal, by the way, but they all made a mess of the aeroplane. None of us really want to be in it. This is the actual hard numbers for 2018. So in 2018 in the US, there were 1,224 accidents. 186 of those had a mechanical reason for why they happened. And 117 of those were where the engine stopped, or which is related. The fatalities were 5. So out of 1,200 accidents, 5 fatalities occurred as a result of the engine failing. So we can say, well, that's not particularly large, but generally speaking, you don't want to be one of them. I think we could all sort of go along with that as a concept. And secondly, this block here, whilst it might not kill you, if you happen to be in an aeroplane when the engine is stopped, it may shorten your life by many weeks as a result of the stress of actually finding your way back to the ground again safely. Now, so these are all the stats, but let's look at what about real experience, and in this case, a sample of one, which is me. I been running the flying school or been associated with the flying school for about 10 years. And in that 10 years, we fly about 3,000 hours a year. So 30,000 hours have been flown in the flying school, and we've had no failures in flight. The only example I can actually think of in those 10 years is a cylinder, and this was last year, in fact. A cylinder came off on one aircraft on approach. However, the pilot taxied in and reported, he didn't report the cylinder had come off, he looked at the cowling, he said there was a lot of vibration on the approach, and reported an oil leak. In fact, the cylinder was literally hanging off on the engine. But that was not but that was the only incident in the flying school that we've had. So it is an interesting statistic. It sort of bears out some of the data that's come out of the US. As an individual, me, not associated with the flying school, I've had one engine failure in 2,000 hours of flying. Timothy, I don't think he's on the call. He cheats because he has two engines in most of his flights, and he's had, I think, 5 in his flying time. But the numbers, and then the only other one I can think of in PPLI that I know of was Matthew Levy, and it wasn't actually him. It was a PA 46 that threw a, I think it threw a conrod through the crankcase. Anyway, we'll come back to that. So the numbers are small, but why do they quit? Why do engines quit? And here is the data on what causes engines to actually fail. You may be surprised to know that in 1/3 of cases, nobody knows. You get the aircraft on the ground, fire the engine up, and she starts perfectly. This is usually contrary to the expectation of the hapless pilot who's desperate to be told that there was something wrong with the engine, rather than maybe his failure to use the carb heat. Most of these are probably the ice fairy. In fact, in my particular instance, I have to admit that was probably what happened when I had an engine failure. The engine stopped on a descent as I was trying to level out to drop into a small airfield at 1,000 feet. By the time I'd worked out that the engine had nothing, I was basically down on the ground. But most of these are probably carb icing. The biggest one is failures is fuel and running out of fuel in various ways. It's not technically an engine failure, but the engine has stopped. So it's nothing really wrong with the engine. It's usually the pilot has made some sort of mistake in calculating what goes wrong with fuel. So it's switching to an empty tank, not putting enough in, miscalculating. Water contamination is a big one. I've had an example where water stopped an engine in flight for me and then restarted, and that was the fuel cap leaking. There's no ring on the fuel cap on the TB20, and that stopped. But it then started again, fortunately. Is the fuel switched on? I would like to say that this has never happened to me, but I would also like to say I'm dating Lily James. Both statements would be equally true. I actually did, in fact, nearly kill myself by trying to take off the Cessna 210 with the fuel off. And it's amazing how long a Cessna 210 can fly. The engine can run and go through a power-up check before it actually stops. So I'm not. So this could happen to everybody. Then are the ones that we're interested in, which are this slot, structural and maintenance issues. Which is maintenance, which is structural. Often it's really hard to find, but we'll try. So what are the causes? Well, we don't have any data on what are the things that go wrong. These are all listed in the accident reports. And if you talk to Rod, he'll tell you that's basically everything that sits in the engine. So essentially anything that's in the engine can go wrong and does go wrong. What we'll do is we'll go through those and just try and understand what are the things that can go wrong and what we can do about them. Before we do that, let's do another little poll here. So the question here is which engine is likely to fail the most. So first of all, let's see what engines people own, and then we'll come back to that question. So let's have a little poll. So let's do the next one. Craig, can you set that one up? Craig, you still there? Seems like we lost Craig. Here we go. Let me just try. I'll try it then. Right.
Yeah, sorry, Jim, I lost my connection then for a second.
Right. I've just launched it. So how are we doing? We've got 30.
Yeah, and David reminded us to read out the answers at the end because they don't show in the recordings.
Yeah, well, yeah. So it's 44 out of 48. I'm going to end the poll now. And yeah, we've got Lycoming is the big majority, Continental 30%, a couple of Rotex and some others. So let's, oh, I didn't share the results. There we go. Sorry, my apologies. Everybody see that? Yeah, it's good. So which ones fail the most? Well, is it Continental or Lycoming? And the answer is neither, it's Rotex. Now, again, health warning on these numbers, they're based on very small numbers. And it's not done on the basis of ours, done on the basis of 1,000 engines. So quite why, so one accident can swing these numbers one way or the other. The Continental probably is a real thing more than Lycoming. And my guess is that this is because Continental are pretty much all the bigger engines are Continentals, so the bigger airplanes are more complex airplanes. The turbo aircraft are mostly Continental. And also Lycoming's, the training fleets are predominantly Lycoming. And they tend to be more reliable. So I think that's probably real. So let's have a look a bit more detail at the engine and the key parts and which are most likely to cause problems. So go back to this chart. Here's a description of, this is basically most of the parts as I discussed. So let's look at the different parts of an engine for those who are not so familiar. For those who know exactly what an engine looks like, bear with me, please, while we go through this section. So here is an engine, a complete engine. Let's start with a complete engine. This is the first engine that I owned. It was from the Cessna 182, an 0470U, 6-cylinder, horizontally opposed, 2 valves per cylinder, and normally aspirated, normally carbureted. So 6 cylinders and with a normal carburetor on it. 230 horsepower. This is the second engine I owned. From the TB20, this is an IO540, another 250 horsepower engine, 6-cylinder. This one is an injected engine. So some of the parts that you can see on here, which I shall try and, can you see that? Is that blown up a bit?
Yeah, it has.
Yeah. So here we've got some of the parts that I'm going to be referring to later that you'll see inside. This is the cylinder, obviously. Here are the push rod tubes which hold the push rods. Here is the constant speed unit. Here's the starter motor and the flywheel starter ring. These lines here, this is the fuel distributor for an injected engine. And these are the fuel lines that go to the injectors here and here and here. That's what an injected engine looks like compared to the carburetor engine which doesn't have those on it. These are the baffles that seal the air coming into the engine, and obviously the air flows in this way and then goes down between the cylinders. However, we'll come onto temperatures later. This distribution of air, the front cylinders, this is 1 and 2 cylinders, are always cooler than the ones at the back, because they tend to get hotter air from the other cylinders. So keeping a constant temperature in the cylinders is difficult with these sorts of engines. Okay, so let's do a refresher on what the inside of an engine. So here's the typical 4-stroke engine. There are 4 strokes: the intake stroke, where you've got the intake valve open, fuel and air is coming in, piston is going down. The compression stroke, the piston is now coming up, both valves closed, spark at the top. Explosion, down comes the piston on the power stroke, and then you get the exhaust stroke with the exhaust valve open. Let's look at that in real time. So this is an engine working, and you can see this is not an aircraft engine. Anybody who knows anything about aircraft engines will immediately say not an aircraft engine, and because it has camshafts, overhead camshafts. This is how a camshaft works, by pushing the valve down. I've never seen an aircraft engine with overhead cams, but Rob will tell me there is one, I'm sure, somewhere. But you get, again, you can see how that goes. This is the sump, this is the crankshaft. These are called conrods, and these are the valves, stems, valve guides. In an aircraft engine, this is what we normally get, and this is the pushrod system. The this is the camshaft with the lobes on that we've just seen. That tends to sit side by side with the crankshaft. I'll show you that in a minute. There's a thing called a cam follower, which sits above the camshaft and pushes up this thing, which is a push rod, which moves the rocker arm, which then pushes the valve down and opens the valve, where you've got the valve seat here and the valve itself sitting in. Now, all these things can go wrong in this whole process. This system, the pushrod system, was invented by Buick in 1904 and hasn't changed much since. I'm not sure why it's stayed that way. It seems particularly complicated, but it obviously is more reliable. Otherwise, they wouldn't have left their aircraft engines designed this way. Here's an aircraft engine stripped down. So this is all the parts of an aircraft engine, lots of different parts. I'm not going to go into detail. This is how an engine shop organizes it. So here's the pistons. Here are the rocker arms that we've just seen the description of. Here are the push rod tubes. So here are the push rods. Here are the tubes they go into. Here are the cam followers. Here's a cam. The camshaft is here. Okay. In the background, you can see the crankshaft. Now, the crankshaft itself, this is what a crankshaft looks like from anybody who hasn't seen it. This is the main journal here, the rod journals here. The pistons get attached to these journals here. So, sorry, the rod journals are here. Sorry, my apologies. This is the main, these are bearing journals here and here. They do fail. So there's quite a lot of examples of crankshafts failing. It's a big chunk of metal. If it fails, the engine almost always stops. Why do they fail? Well, there was a lot, usually lubrication. It's run out of oil. The channels in the crankcase are blocked. There have been a spate of metallurgy failures, particularly in the 90s. Lycoming had a batch of failures of the crankshaft. Corrosion, another cause. And probably one of the big ones is prop strikes and shock loading where it's damaged. Corrosion, I've had personally I had a crankshaft fail, didn't actually fail in the air, but when it was being overhauled, it was failed because it had corroded the aircraft it came from and sat in a field for 3 years. And when they do fail, they're pretty expensive. Next part to look at is the crankcase. This is half a crankcase. When you split the crankcase, this is what it looks like. This one's been cleaned. The crankshaft fits in this well here. In here, this is a main bearing, sits in this well here for the main journal, and lubrication comes through galleries in the crankcase and come through these holes in the main bearing here, and you can see these grooves here. It all comes through here and then lubricates the crankshaft. Here's the other side that sits on the top. There's an equivalent part of the crankcase which comes the other way around, and they're bolted together through these through studs here. And the through studs are all over the case, which hold the crankcase together. Crankcases fail. The main failure is fretting. So what happens is these are held together by nuts, these bolts. Over time, they get gaps in them. The case rattles and slowly wears away, just to the point where it's not holding the bearings down. The bearings that start to rotate. Once the bearing starts to rotate, the engine will fail fairly rapidly. There are other issues which I'm sure Rob could explain as a result that are caused by crankshaft failures, and they do crack as well over time. Here's a crankshaft with the rod journals on, con rods on, attached to it, ready to go into a crankcase. Here's a camshaft. This is what a camshaft looks like for real, with the lobes on here. You can see the lobes, and here are push rod tubes. Here's a camshaft, and cam followers, which are ours from failing. This is corrosion. You can see here on the camshaft. The camshafts are coated and hardened, and have a thin layer of hardened metal on them. As soon as that breaks down, the camshaft is going to disintegrate and will very rapidly be followed by an engine failure. Here is the pistons. They don't fail particularly much on their own. The rings around the pistons, will come back to that. There are 3 on each piston. Here are the con rods that attach in here on the piston, and these are the clamps that hold the con rod onto the crankshaft. Piston, if you haven't seen the piston, this is the inside of the piston. Here are the 2 valves. This is a valve this is a piston that's in need of cleaning. Here's the slot where the spark plug goes in, and there's another one on the other side. Cylinders don't come apart very regularly, but sometimes they do. Mostly as a result of shock cooling or bad treatment. This is where the spark plug goes in, and they often crack here or here. But if the cylinder comes off, generally speaking, the engine can still run if it's just one of them. Here's a particular photograph of the valve, in the seat here. This is the valve guide. I've had a situation where the valve guides on the engine weren't put in correctly. When the engine was overhauled, it went 90 degrees, and there were gaps in the valve seat. Here's a half assembled engine. Here you can see now where the camshaft fits and how the crankshaft fits in there relative to each other. And here's an engine being assembled without the pistons on. And here is where the push rods will go, and the push rod tubes. So all of these parts can fail. Here's an example of what's happened when a con rod fails. It makes a pretty nasty mess of the crankcase, and the result of this will be an oil shower over the windscreen and to some unsuspecting individual on the ground. It will just drop all the oil out of the aircraft and will vibrate very badly, and unless you switch the engine down, it will shake itself probably off the engine mounts, which will make sure that you will not be able to glide it down to the ground. So if such a thing happens, the engine must be stopped straight away. So Here's another example. The rod piece pieces come through here. A number of possible causes for these: fretting of the crankcase, bearing failure, oil blockage on the crankcase. These can all cause a rod to fail. So that's a run through of what an engine looks like and the sort of things that can go wrong with an engine. And we're going to do another poll. And this now is the engine failure one. Shall I do it, Craig? Are you still there? Or?
Yeah, happy to, or happy to lead to you. Yeah.
I'll do it then. Right, so what I'm asking here is, has anybody on the call experienced a engine failure? All right, so that's what I'm looking for.
And between us, Jim, we've got 46,000 hours of flying experience.
46,000, okay. I should have said in flight. I hope that's okay. Let's just end that and share the results. Quite a lot, actually. So we can be sure that none of them resulted in a fatality. So unless somebody is here in a ghostly apparition, but
do you want to just read out the answers, Jim? Just
yeah, let's have the answers. Have you got it?
Yeah. So of the 42 people who submitted, 29, nearly 70% had no engine failures, experienced 9. 10 people have experienced 1 engine failure, which is about a quarter. 2 people have experienced 2 engine failures, which is 5%, and 1 person was unfortunate to experience more than 2 engine failures.
I just wonder if Timothy's on the call, because that could be Timothy. But the yeah, that is interesting, isn't it? So that's way above the numbers that have been quoted from the AOPA statistics. So it'd be interesting to think that through. Anyway, so now let's just have a short break and see if there are any questions at this stage. So,
None have come through to me.
have we got any questions at this stage?
No, nothing's come through to me. Anything direct to you?
Yeah, I've got one, which is, I guess it's primarily addressed to those who have had engine failures. What were the warning signs before the failure actually occurred, or did they come straight out of the blue?
Anybody want to volunteer? Mine was a fuel one, so an icing, so it took me by surprise.
Mine was engine vibrations because a valve went, a problem with one of the valves.
So you shut it down, did you?
Yes, and luckily it was a parachute aircraft and I was above the airfield, so I just came to circle down to the and landed uneventfully.
Oh, right, okay.
Mine was fortunately downwind and the engine suddenly went. I had no warning at all.
Mine was loss of oil pressure on one engine and just shut that down. I was over the sea, so it was a good job I had another engine.
Yeah. I
Well,
think
it was it was my case also with oil pressure going down, and I was in downwind, so I managed to land without any problem.
Yeah.
I guess I should explain that what was behind my question was to understand whether engine health monitoring can help predict and therefore avoid failures, or whether most of them are unexpected and unpredictable. Because compared with what is available on car engines, let alone gas turbines these days, our engine health monitoring system, so certainly installed, is next to zero. Temperature gauge and a oil pressure gauge is about it.
Yeah.
Okay.
Okay, there's a question here. What stage do engine failures mainly occur? There is some data again from America that in fact is pretty equal between takeoff and cruise. So which is rather strange, because you'd expect, because cruise is much longer stage of flight than the takeoff phase, you would expect more to be from the cruise phase. The other interesting factor in there is that the fatalities are roughly equal. You'd expect more people to survive from the cruise than from the takeoff phase, but that's not true. They go together. Just going back to the numbers, when I first set up, I did say that when looking at the data, the engine failures are not, how many engine failures are not reported as accidents. So the AOPA numbers look low because probably there's a large number of engine failures that are not reported in the accident statistics. I just wonder how many of the ones that we've talked about here, or people have had them, have actually registered them with the AIB or anything, you know, that they got on the ground, oh, I'm glad I'm alive, take it over to the engine shop and get them to fix it. But it doesn't appear in the accident statistics as such because people survived. So that may be one of the reasons why that's happened. Okay.
Jim, sorry, did you get David Chambers got a question? I wondered how many were in IMC.
Oh yeah,
and parent.
Yeah, I don't know. I mean, there's no data on that from AOPA. So an engine failure, I mean, depends on how many times, how often are you actually in IMC for how long? I don't think it knows whether it's in cloud or not. So it's probably just a factor of how much flying is done in IMC. Per has his hand up. What did Per want? Per.
Yeah, I just want, you didn't talk too much about the magnetos, and I know we have two generally, but how often do they fail?
Yeah, I think the reason you don't get many magneto failures because there are two. The chances are of both failing simultaneously about 1 in a million. I just had that calculation done because my engineer said when I put an engine in the other day that both had failed. I said that can't be, it's impossible. And I was proved to be right. It wasn't, it hadn't failed. So yeah, so I don't think magnetos put the aircraft on the ground, from the air rather, should I say.
Graham's got his hand up, and John Davies got a question. What percentage of failures are soon after maintenance?
Yeah, don't have any data on that. Rob, do you have any idea on that, or Graham maybe?
No, I personally don't know, Jim.
Graham might have some, but
not really data on how many immediately after maintenance, but my comment was going to be more on I think you mentioned about engine monitoring and how many engine failures are spotted by engine monitoring. We actually get quite a few people with good engine monitors who alert and bring in the aircraft for investigation when they spot something not quite right, and that probably prevents engine failure in flight quite often. Because you see early on a sign of something trending. So it doesn't necessarily, aircraft that fail in flight have had a warning on an engine monitor, but warnings on engine monitor, I do think, contribute to preventing failure in flight.
Okay, I've got a section on engine monitors in a minute, so hope we can perhaps come back to that as well, Graham. So
Chris Bishop's hand up. Jim, I don't know if you saw that.
Who's got his hand up?
Chris Bishop.
Yeah, Chris.
Oh yeah, just a quickie. There's a Mooney 201 Golf Mike Alpha based at Cambridge. I've had shares in it twice, but after I sold my share the second time, it suffered an engine failure at about flight level 100, I think, in the airways. and landed at a military base somewhere, I think just one of the ones just south of Newcastle. And it was a magneto failure caused by the fact that both magnetos are bolted onto the same plate, and the mounting screws hadn't been fitted properly during maintenance, and so the plate fell off and both mags failed. And the pilot did a fantastic dead stick landing into a military base. So magnetos can cause an engine failure. I think the engine's since been replaced with a modified variant which has the magnetos mounted separately. Just an FYI.
Yeah, actually, interestingly, my 182 had a similar setup. It was a twin magneto, but one drive. And I thought, what the hell is the point of that? If the drive goes, then you've lost both magnetos. So I was never very comfortable with that arrangement.
Yeah, no, it's a good point. Sorry, Graham here again. You're right. Having two magnetos when they are separate magnetos is great, but you do have aircraft engines with dual magnetos where the two are linked, and then you don't have quite the resilience that you expect.
Yeah, so that's informing that. Okay, are we good to go?
I mean, the only thing I would say to you guys is, this is very difficult, obviously, trying to watch out for something before it happens. Definitely the engine management system is without a shadow of a doubt the largest leap forward forever. But one thing to monitor, particularly on Lycoming engines, is, and this is going to seem a strange thing to say, is the position of the propeller when you switch the engine off. Now, the reason for that is it should finish at 10 to 2 or 20 past 4. That is the normal position. If the prop finishes at any other position, then it's quite a clear indication of crankcase fretting, because what it's doing is the internal resistance of the engine is effectively grabbing the crank, so not allowing it to freely run. So if ever you guys switch your engine off and the prop finishes at 12 o'clock, 6 o'clock type of position, that's something to not to overlook.
Is the same true for 3 props? Rob, how would you work out for that?
I'm sorry?
What about 3-blade, Rob?
Well, again, that's slightly harder, but you normally finish with the top blade at the top, so it's just a compression stroke thing. You just want to look out for irregular stopping patterns. Let's put it that way. But that's more particular to Lycomings and Continentals. Continentals don't suffer nowhere near the degree that Lycomings suffer.
Good. Okay, so let's move on because I'm going to be running out of time for sure.
Yeah, sorry.
Okay, so we're now going to talk. So we've covered some of this already, but we've already established that the risk of engine failure when you start is not high, but obviously it's not insignificant, and there's quite a few examples of engine failures we've already discovered on the membership here. So what can we do to reduce the risk? So this is the next section, and just a reminder that these are the items that cause failure. Firstly, the first thing I would say about reducing risk is fly the aeroplane. If they stand around and don't get flown, they will corrode. There's a good reason why flying schools have a good reputation in safety, and that they don't have many engine failures is because they fly all the time. Next, let's talk about fuel. Make sure it's switched on, know the fuel system, always check for water, check the O-rings on the fuel caps. So that is, and that comes from my experience as well. The reason I got water in the fuel was the fuel caps, there's O-rings on the fuel caps, they had degraded. If you're a carbureted aeroplane, non-injected, always use the carb heat. It's interesting that half the icing failures apparently had instructors on board. So it's a sure way to turn a simulated failure into a real one by not using the carb heat. If when you're pulling the carb heat on, you don't see a drop, I would check the cable that is actually working and is moving the carb heat. Oil, don't fly without any oil. You know, obviously it's stupid to say, but I see a number of occasions where people let the oil run down. So make sure there's the oil there. Pressure, react if the pressure changes, react. So either high or low, react if there's an oil leak. Yeah, the oil leak may be benign, and maybe just a gasket leaking, but I have seen situations where I thought, oh, that's not, not worry about it. Got it into the shop, and it has been an engine, a failure about to happen within 10 or 20 hours. So pay attention to leaks. When you do an oil change, always check the filter. Sure sign that something is going to go wrong is metal in the filter. Personally, I always ask the engineer to show me the filter. I don't always trust that they will look hard enough. And if it's my engine, I want to see. Next one is definitely pay attention to mag drops. A failed plug can lead to pre-ignition, and pre-ignition we'll talk about that later, but if we get time, will cause severe damage to a piston cylinder if it happens. And Colin, I think we had an example of that on one of our trips. I remember sitting in Shvardshire Hull in a beautiful, very nice restaurant with a beer, poring over engine monitor charts as to why one of his cylinders was heating up to 500 degrees F, and we couldn't actually work it out. It turned out that it was a plug, and he was getting pre-ignition on that cylinder. So always pay attention to mag drops, and if there is a mag drop, don't fly the aeroplane. And a mag drop you can't get rid of. Normally you would get rid of it by running it lean for a bit. If it doesn't recover, then don't fly the airplane. If the performance changes, if you get during flight, if you find that you're not getting the performance you want to, that's a sign that something's happening. Cylinders going or something of that ilk. So these are all routine checks that you can do all the time when you're flying, and are useful reminders. I'm sure we're all doing them, and we should. I don't need to say this, but that's usually when something starts to happen. Then there are the more preventative type of things that we can do, and we've already talked, and Graham's already mentioned the engine monitor, but there is look at oil analysis, compression testing, and the last one, don't skimp on maintenance, and Graham told me to put that one in at the bottom there. So let's look at oil analysis. This is a system where you, after every oil change, you get the oil analyzed. One analysis is not good enough. You have to do trends. Personally, I don't do it, mainly because I don't have the self-discipline to go through the oil analysis. Some people swear by it. The element that is in the oil analysis that is trending will usually indicate what particular part of the engine is failing. So that I mean, we can't have got time to go into it, but it is definitely a predictive technique if you've disciplined enough to do it. Compression testing. Now, those who don't know what compression testing is, just a brief explanation. You take a cylinder, you take the plug out, and you inject 80 psi air into the cylinder, and you measure how much of that 80 psi is kept in the cylinder. Now, 80 psi goes in. There's no engine on the planet that will hold the 80 psi. It will always leak a bit. But if on a Lycoming engine it drops below 60, you don't fly the aeroplane, and if it drops below 50, you don't fly the aeroplane. The air will leak usually past the pistons. So if through the rings here, if it is leaking through there, an experienced engineer can tell you by listening to the sump. He'll hear a hissing noise coming through there, or alternatively looking at the valves here. It's leaking through a valve. If you listen through the exhaust port, you'll hear a hissing through the exhaust port. So that is a way you can tell what is going on within each cylinder. Now, every time I've had low compressions and I pull the cylinder, this cylinder is in need of repair and is shortly about to go wrong, particularly if it's an exhaust valve. So I'm a great believer in this, probably mainly because I've flown behind Lycoming engines. Graham is not so keen on it as me, mainly because he flies Continentals. The big bore Continentals are definitely, it's probably less diagnostic, but even here I would check a cylinder out if it drops below 50. Engine monitors, Graham's already mentioned engine monitors. Here's some pictures of some, let's just go back. This is, these are some engine monitors of JPI. They are the market leaders in engine monitors, but pretty well everybody else. So they're now appearing in most avionics systems now. And personally, I wouldn't go anywhere long distance with an airplane without one of these on it. Here's an example of some displays from an engine monitor. This is a 6-cylinder engine monitor, engine. And we could spend a seminar actually going through how to use one of these. And these slides did come from the advanced engine seminar that we had in Belgium. And we spent half a day just on engine monitors and how to use them, how to interpret them. But a brief look here. This is a 6-cylinder. You can see the 6 cylinders, 1, 2, 3, 4, 5, 6 at the top, and it's turbo. There's a turbine inlet temperature here. The height of the top is the exhaust gas temperature, and the black bar is the cylinder head temperature. In this particular instance, the dot will tell you down below, this is the actual number for each cylinder. So in cylinder 2, you've got a exhaust gas temperature of 1458, and this is in Fahrenheit, and 346 on the cylinder head temperature. Here's a different display. We've got this is showing the differential between the hottest and coldest cylinder. And here you can switch the display to tell you what your battery is doing. You can also have fuel flow, a whole series of different things. Okay, so here's something going wrong, and what's going wrong here. Here's now what it was. This is in 5-minute intervals. Here is a display after a minute after this one, and then here it is a minute after that. So it's a bit of fun. Let's try a little poll, and if somebody, see if you think, I'll leave it up there for the minute, and you need to think of what might actually have gone wrong here. So let's do that. So
I've launched that, Jim. I've launched that.
Sorry?
I've launched that poll. So.
You've done it. Okay. Is it launched? Right.
Yeah. How do you explain this chart? Cylinder failure, exhaust valve, injector blocked, magneto failure, spark plug. I don't know if you want to go one slide back, Jim, just as people answer.
Can I go back with that?
Right.
There we go.
So we've got about 13 response. Find a few more. "34 people responded, 35.
It is anonymous, by the way, so you don't need to worry about making a fool of itself. So.
37.
That's good.
Do you want me to
Yeah,
end
let's
it?
end it there. Let's end it there. So,
And share the results? There you go.
and I think you passed.
So,
Yeah,
just about the stats there, Jim. So 14% said cylinder failure, 14% exhaust valve. The majority, 43%, said injector blocked, 3% said magneto failure, and 27% spark plug.
good. Anyway, the answer was injector failure. Okay, injector blocked. All right. So, but anyway, it's just a bit of fun. So that there are lots of diagnostics. So there are lots of examples of how this how to use an engine monitor to tell you what is going wrong with your aeroplane. Okay, so here, for example, have you got a red line through?
Yeah, we had that last time. I'm never quite sure how you clear them.
I think it's here. Erase, no, I can't get rid of it. Anyway, it's there. This is an example of an output from an engine monitor, JPI engine monitor, which shows over time. This is all this stuff down here is the engine starting up and warming up, and this is where it's cooling down when it's shut down. But this is the cylinder head temperatures, and this is the exhaust gas temperatures, and you can track over a flight what is going on. And this is amazingly good for diagnosis when you haven't had time to look at it in the flight, and is essential when it comes to operating lead and peak. Okay, so let's move on. Now I've got 20 minutes. Should we just take some questions here before we go on to this section? Any questions from that section?
Lots of suggestions how to clear the annotation, clear the lines of it. Yeah.
Can you get rid of it?
Yeah, I think people are saying go on view options, annotations, and have a waste bucket, or under the share screen view options at the top of the screen, click clear all drawings, but we'll see.
I tried that and I couldn't get it to clear.
Can I ask a question, please?
Yeah.
So, how easy is it to check the condition of a camshaft with a borescope?
Rob, I don't think it's easy for the borescope. You can do it. The best way is to take a cylinder off. So.
Yeah, it's you can't see the camshaft when you camshaft for the lobe when you carry out a borescope. The only way that you can do a very rough check is to take the rocker cover off and do a rotation and check the lift of the lobe. In other words, what the actual valve is opening against another. There is numbers for that, but the only 100% safe way is to take cylinder off and have a look round. But you know, I do think what gets missed on 80% of occasions, and I don't know why it gets missed, is maintenance companies do not check scavenge filters, and that is the first sign of a camshaft failure. But they just, a lot of them don't even know these filters exist.
Okay.
What I mean by, I'll explain what I mean by scavenge filter. So everyone looks at the filter because it's the main filter is the pressure filter, it's an element filter, and that's part of routine maintenance. However, there's another filter which sits in the sump, which is removable on Lycoming engines. It's visible on Continental engines, and they very rarely ever get taken out. And what that filter does is the contaminants for the cam go into that filter first before it enters into the oil pump. And if you pull them filters out and you start seeing slivers of metal, they're the first indicator of cam failure.
Okay.
You'll get metal on the oil filter as well, won't you, Rob?
As a secondary, you will, yes, but you've got to understand that the the elements and the contamination has gone through the pump, through the engine, into the bearings, and ends up at the filter. So the degree that you're going to get is going to be relatively insignificant as to the size that you would get in scavenge filters. So, you know, next time you're in your maintenance company and they're doing a 100-hour check, ask the question, say, how clean was the scavenge filter, and see how they look at you and see what their reaction is. And like I say, it's pretty shocking that a lot of them don't even know it exists. But anyway.
Yeah.
Yep, exactly as Rob says. 50-hour check, just the oil filter. 100-hour check should always be the scavenge filter.
Okay, any other? Now, I've got a decision to make. The next section is pretty data dense, and I've got 20 minutes to do it in. So what I'm going to do is gallop through it, and if people are interested in following up in more detail, we can maybe do another session where we go, because I think we need a hard close date. Okay, so everybody okay with that?
Yeah.
All right. So let's know what's happening. Sorry, I'm missing. So let's just remind ourselves. This is the what's the 4 strokes. Just around top dead center. Remember that the piston is very non-linear. It doesn't move very much at the top. Now, I'm going to introduce 4 concepts before talking in detail about what we do about running. So this section primarily is about running lean of peak. Now, here's a chart of what's going on inside a cylinder when we run through a four-stroke cycle. This is the compression cycle. Here's the spark. As the fuel ignites, the pressure builds up, reaches peak pressure, and then drops away as the burn drops off. The cylinder is starting to move down here. So this is the full 4-stroke, 2 engine revolutions. And as a pilot, we can influence the yellow area with use of manifold pressure, RPM mixture. Second concept is the strength of aluminium and temperature. Some of you may know this. This is tensile strength of aluminium based on temperature. At 450 degrees Fahrenheit, we are less than 50% of the tensile strength of aluminium. At 500 degrees Fahrenheit, we're now down to about 25%. And, somebody's got rid of it. And the most of both Lycoming and Continental say that you can operate, the red line is 500 degrees F. Now, most of your cylinders are made of aluminium. Now, during certification, they control the airflow over the cylinders. I showed you what the cylinders look like in the TB20. In a test rig, the airflow over the cylinders is much more carefully controlled, and that's how they persuade the authorities that 500 is okay. In a practical aeroplane, it's never like that. The engine baffling is from acceptable to horrible, and it doesn't improve with age. So in real life, we all, so the belief is, and this is certainly the way I operate, 400 degrees F is the limit for cylinder head temperatures. If it gets to 380, then do something about it. Now, this varies with aeroplanes and what the cowling is like and what the airflow is like. In the 210 that I've operated with Graham, it's almost impossible to keep it under 400 on the climb out. Cirrus SR22 with basically the same engine, I never could get it above 360. Go figure. Anyway, that's that. So the next concept is burn, and what's going on in the burn of when an engine, when you ignite the fuel and air mixture. Here is this example is power on this side, fuel air ratio on this side. This is the lean side. This is the rich side. As you come up from rich down here, it comes to 0%. Power comes up here. you've got maximum power, and then as you get richer and richer, it drops away again. And there's this concept of stoichiometric mixture where every fuel molecule has a piece of oxygen to go with it, and pKg EGT corresponds to this stoichiometric mixture. As an organic chemist, I'm showing you an equation. Graham will like this as well. But this isn't exact. This is a heavy simplification actually, but it explains the concept. Right amount of carbon, right amount of oxygen gives you harmless carbon dioxide. Yes, it is harmless, and water. That in pilot talk happens at peak exhaust gas temperature or lean at peak. Okay, so a rich mixture is where there is more fuel molecules than oxygen molecules. So that's what a rich mixture is, and so it's when there's more fuel than stoichiometric. In that equation, instead of it burning, resulting in carbon dioxide, you get some underburn and you get carbon monoxide created as a result. So on a richer than stoichiometric mix, you get carbon monoxide, which we all know is poisonous. Now, in a lean mixture, there you've got less fuel molecules than oxygen, and this you get a full burn because there's less fuel. You get less energy, and there's essentially less power, and it drops off fairly quickly. So a lean mixture, as defined as any mixture less than stoichiometric. Okay. Now, point of these charts is both very lean and very rich mixtures burn slower than stoichiometric. Now, just going back to this chart, remember over the top dead center, there's very little movement. Now on current engines, the spark is always started at 20 or 22 degrees before top dead center. This is a compromise for a full rich mixture takeoff power and a compromise for cruise power. Neither of them are perfect, they're in between each other. And the burn rate determines where the peak pressure pulse occurs. All right. Now we say when we're stoichiometric, you'll get a very fast burn, so it'll bring it forward. When you use lean or rich mixtures, the peak pressure will drop away. So making the mixture much greener will give you more of a mechanical advantage, because the peak pressure is occurring when the piston is in the downward track, so that it's starting to expand. And the temperature will also be lower. One of the things that I've always found quite difficult to understand is, why the lean mixture and rich mixtures have lower CHTs. Well, the reason is that there's a direct relationship between the peak pressure and the heat transfer between the gases in the cylinder and the cylinder walls. The actual temperature of the burning fuel is around 2000 degrees F. The cylinder walls are around 350, 400, between there. And those temperatures are concerned by the heat transfer between the peak pressure and the cylinder wall itself. The lower you can get the peak pressure, the later you can get the peak pressure, the lower will be the cylinder head temperature. Another factor to remember is that where the peak pressure appears in the power cycle is determined by the RPM. So you have a slower RPM, essentially it will extend the cycle, it takes longer, which effectively means the peak pressure advances, comes earlier, and you counterintuitively reducing the RPM actually increases the pressure. So you can change the timing of how long each of these phases lasts by the RPM, but it makes no difference to the timing, so how long the combustion event takes place. Now there are other factors in influencing burn rate, and which includes what fuel you've got in there. If you've got only one spark, for instance, you'll get a slow burning flame front. Detonation, which we weren't planning to talk about today, but we can get early, and pre-ignition, which is the really damaging thing. Detonation itself doesn't usually cause damage. This usually does. And this is what happened to Colin when he had a cylinder head temperature above 500. Now, these are all concepts which you can't do anything about. This is nothing that you haven't got control of these things other than to understand what's going on. This chart is the classic mixture chart. You may have seen this before, you may not. I don't know how familiar you are with this. But these are the things which we control by using the mixture lever when we play with 3 of our levers, actually. The first one is exhaust gas temperature. This is EGT. This is really a phony temperature. It's only useful for navigating the mixture curve. It's not a real temperature. You can change the actual exhaust gas temperature by where you put the probe, and it can make big differences. So that's the exhaust gas temperature. The cylinder head temperature, this one is a real temperature, and it's a direct reflection of internal cylinder pressures, this one here. This one here, BHP, is the horsepower that is developed. And this one here is brake specific fuel charge, not charge. I've forgotten that, but essentially what that is a measure of fuel economy. So here is the lowest fuel for power ratio. So this is the most economic way, so a point. So this is where best economy sits. Okay, so let's now we talked about temperature, 400 degrees. Okay, if you want your cylinder head temperature to stay at 400 degrees, you've below 400, you've got to stay out of this red box area. Now the hottest cylinder head temperature is where the orange arrow is, which is 40 degrees. So here's peak, and here's 40 degrees Richard peak. That is the hottest cylinder head temperature. Here is the hottest exhaust valve temperature, 25 degrees Richard peak. So you don't want to be running the engine in this area. The reality is, for best power, you want to be running the engine over here, which is about 100 degrees Richard peak. 100 degrees Richard peak is quite a big fuel flow. I mean, we can look at it in pounds per hour, but compared to, so over here, compared to running lean of peak, is a big fuel difference. And it amounts to about 15% less fuel moving between here and here. So these are the 2 places that you really want to be running your engine, either here or here. Now, obviously, here you get a lower cylinder head temperature, and but you get quite a rapid drop off in horsepower. So there's a penalty to pay in terms of power, but you can be running the engine clear. So you can see the exhaust gas temperature is here is just go up. So just go. So here there are 2 places. So on low power, the best economy falls at 20 degrees lean at peak, and when you're on high power, it's 90 degrees lean at peak. Just bear in mind that this is all done at 2300 and 20 RPM and 24 inches of manifold pressure. If it's a normally aspirated engine, and we tend to fly quite high, we won't be operating in this range. When we come up to say 10,000 feet, we've got a manifold pressure probably 19 inches. And these temperatures will by definition be lower because you're running on a much lower power. Okay, so I'm galloping through this. So the advantage, so this is really a pitch to running lean of peak. And personally, I've run most of my engines which have got monitors on lean at peak. And there are safety advantages, less stress on the engine because of lower internal pressures, big fuel saving and extended range, intellectual advantages, if you want to call it that, because you understand much better what's going on. and maintenance advantage. You get less blow by the rings, lower oil use. You get a cooler running, you get less spark plug fouling, and you can troubleshoot valve and ignition problems. The disadvantages, it takes quite a lot to get it to the point where you can run it. Instrumenter, you do have to have an engine monitor. You will lose power, and the engine will require some fine tuning. You need to take certain steps. Now, very few engines will run smoothly leader peak out of the box, and this is the reason. Here's an example. So we've just looked at, when we looked at that earlier chart, we looked at running just one cylinder effectively. Now this is a 6-cylinder engine, and you start here and you start to lean as you pull the mixture back. What you get is cylinder 1 is peaking here. This is the EGT peaking. At this point, you see all these other cylinders are still well below peak, still way richer peak. Then you lean and you get to cylinder 2 peaks, then cylinder 3 peaks here. Now, if you come down to, and you get to the last one peaking here. So this one is coming in at a particular fuel flow. So you get a range here. When this one is peaking here, this one is way leaner peak, okay? So the first one that is that reached peak is now down here and has probably actually stopped running. So it's now, so it will not be a smooth engine when you're down here. And the only way you can get to run leaner peak is where all these cylinders are operating in the same way. And this is what has made GAMI, the injector people, a fortune, because that's what they do, is they work with people's engines and tune the engine. So you get, it only works with injected engines, by the way, as well, so that they sit within 0.3 US gallons per hour range, so that you can run smoothly leaner peak. So it takes a bit of effort to run leaner peak. My TB20, I got it to run leaner peak. The Cessna 210 will run leaner peak. It's nicely balanced. You get a better fuel economy and range, but it will take you a bit longer. Lower maintenance costs, and it's safer, no carbon dioxide. So questions about that? So I'm sorry about that. I should have, by the way, I should have acknowledged that those slides have come from the Advanced Engine Management course run by John Deakin and George Brayley, George Brayley is the guy who invented or who set up GAMI Engineering. That's nothing to do with Gamma. It's a completely separate company, nothing to do with Rob. That his business is all about how to get an engine running lean at peak. All right. So if you are interested in this sort of stuff, I recommend you Google a thing called Pelican's Perch. This is where I certainly picked up, and I still go back to it a lot. Pelican's Perch is George Deakin's basically website, where he goes through many articles on how running engines in this way works. Okay, end of that section. So I've got 1 minute for questions.
Thanks, Jim. I think, like Eleanor was just messaging, if people want to stay a bit longer and ask questions, some complicated stuff there, then I think you're happy, aren't you, Jim, to stay a little bit longer?
Yeah, I'm happy to stay longer if people want to, yeah. I can go back and spend a bit more time on it. If anybody wants to stop, then it's fine.
A question from David, would you run lean of peak without GAMI injectors?
No. Well, sorry, I say that's maybe wrong to say. Some of the Lycoming injectors systems and the Continental systems that I've run with didn't have GAMIs on, and they do actually, they were pretty well balanced. So I did manage to get them running lean of peak. But I've also been in aircraft where there was no way. I couldn't even get it past. I couldn't even get down to peak EGT. So and then they'd have to ended up having to run them rich all the time.
I'm sure my training on my PA28 had me pulling it back lean until the engine spluttered and then putting it a little bit further forward, if my memory serves me right.
Yeah, but there you're still well rich at peak. You can't do it on a normally aspirated engine. If you actually look at the fuel distribution, so the air, so it's all about how evenly distributed the mist of fuel and air is. And on a normally carbureted engine, again, this is all done in the advanced engine course, they showed microscopic pictures of the droplet size from a carburetor compared to an injector. And the droplet size is all over the place with the carburetor. You've got huge ones and you get little ones. And the distribution that you get as on the inlet manifold is massively different. So you can't get them to even up. What you're doing when you run rough is you're basically having the first cylinder go out, right? The other 3 cylinders are probably running rich. Now you richen it. You bring the 1 cylinder maybe is on stoichiometric. The other 3 cylinders will be running rich. So that's so you're not running at peak by any means on those. The only way you can sort of get near it with a normally aspirated engine is to stick the carb heat on, because what you're doing there is heating up the air, and you're evaporating some of the big droplets of fuel, so you get more even distribution of fuel and air, and there you might be able to get it to work, and you can then run much more economically that way, but you've obviously lost power doing that.
Okay, thank you. And a question from Lauren Schuler is, what about lean of peak with a carbureted engine?
Just talked about that.
Yeah, that's the same thing. Cool, I thought so.
Can I ask a question? I don't know if I can be heard or not. But
sure, yeah.
Hey, Stephen, yes, we can hear you.
Hi, one question I was going to ask. I mean, I manage an R182 to run quite comfortably without gummy injectors. I did actually a check recently, and we have about 0.4 of a gallon per hour between the richest and the leanest, and it works actually very well for the cruise. The question I had was about the climb. Now, I understand why you wouldn't run necessarily lean at peak in the climb, because you're running at pretty, major power settings, and obviously then the temperatures and the peak pressures are going to be way high. But how do you lean in the climb? Do you tend to lean by using one of the cylinder's exhaust gas temperatures in order to lean to that as you climb? Do you do it by feel, by instinct? How do you do it?
No, it's fairly well established how to do this. So what you do is, when you're on the ground, and I'm assuming you're at sea level, when you stick full power on, check your exhaust gas temperature. So if your cylinders are well balanced, the exhaust gas temperature should be roughly the same. Okay, they may be 10 degrees, 20 degrees different from each other. So note that down, note what that is. And then when you climb, and usually I would do it at around 3,000 foot intervals, I will lean back, so it will now get hotter, okay? So as you're climbing up, the exhaust, as the manifold pressure reduces and the air gets thinner, you're getting less oxygen, you will get, you get cooler, sorry, my apologies. And you just tune the exhaust gas temperature to the same temperature that you were on the, when you're on the ground, it's at 0 feet, okay?
And that's it, you just keep that all the way up, yeah.
So each time you're going up, bring it back to where it was when you were on the ground.
Okay.
Now you're not going to get, so there you're not going to so as it goes leaner, so it goes richer as you climb. So you will get a drop in EGT, okay? So you can now bring it back up to the EGT that it was on the ground. You will not overlean it and you will not overheat it, because that's exactly what the mixture ratio was on the ground, if you follow the logic of that.
And there's no danger that you're going to get into sort of red box territory like that. In other words, you're not going to be within that 25, 30 degrees rich of peak, which is a danger area, particularly at high power settings.
Yeah, well, don't forget, as you're going up, your power's going off.
Yeah.
So you're getting lower and lower power. You still doesn't take away the need to keep your engine, your cylinder head temperatures down. So if your cylinder head temperatures are creeping up, you've got to do something about it. So you can leave it where it is, but essentially what you're doing by leaving it where it is you're reducing power. So why waste fuel? You might as well just reduce the power and leave it. If your cylinder head temperature are going up, what I do is I push the nose down and get greater airspeed, so that you get more airflow over the cylinders. That would be my technique in that area. But generally speaking, I find it's not a problem. Once you're above 3,000 feet or so, manifold pressures are dropping anyway. I assume you're not turboed. Are you turboed?
No, we're normally aspirated.
Okay. So in a normally aspirated engine, your power is reducing as you climb anyway. So the engine should normally cool.
Yeah.
So what is temperatures in the climb normally?
Sorry,
cylinder head temperatures.
We had a real problem actually at one point with that, and then we did a bit of work on the baffling. Actually, I mean, when you mentioned baffling, it's absolutely critical that, because even the tiniest kind of gap can make absolutely all the difference. So at one point we were getting well over 400 Fahrenheit in the climb, particularly on I think 2 cylinders, and then we got the baffling rechecked. I just can't emphasize enough how important that is to do. And we actually found that the cylinder head temperatures came down. Now, obviously with cowl flaps open, we're managing them at about 400. We set one of those on our JPI, we set one of our user customable alarms at 400 Fahrenheit. So although obviously the homing limit is supposed to be 500, when we hit 400, we have it goes into the red and it flashes. So we're kind of aware of it.
Yeah.
It's made all the difference having the monitor. I mean, it's literally changed the way we fly the airplane now, actually.
Yeah, I absolutely agree. I mean, I can't fly without them now. Eleanor, you raised your hand. Did you?
Yes. First of all, thank you very much for a very detailed presentation. Excellent. I can see your time at Unilever doing presentations served you well. Although you were doing them to the board, but never mind. We have to come down from the top sometimes. So I have a clarification and a question. So you explained that it's very rare that both magneto would fail, but then when you went through the checklist, you said you should not fly if one of them is not working, if you can't lean it, clean it. Why is that? Maybe it's just I haven't heard or understood exactly why.
Okay.
If it's such a rare chance.
Yeah, 2 reasons I would say. One is if you've got a mag drop, one of the magnetos could not be working, so you're now down to 1. All right. So but the primary reason is if you can't clear it by running lean, then the chances are, and nearly always is the case in my experience, you've got a plug problem. And if you've got a plug problem, you can get pre-ignition. So you'll get a glow plug effect if the ceramic, for instance, is breaking away from the main element of the spark plug, and this can destroy an engine pretty quickly.
Okay, and my question is, I'm flying Grumman Tiger. Actually, it used to belong to one of the people on this call. I don't know if he's here, Mr. Bowles. But when I'm using the carb heat, the engine sounds a bit rough. So actually the plane, we almost never, we own this place for people, 5. We almost never use the carb heat because it doesn't seem to need it. And when we do, there is the engine doesn't run smoothly. So I don't know, is it just, something we should be worried about, or?
Well, what happens when you put the carb heat on is it goes rich. All right?
Yes.
It goes rich. So first thing I would question is what's the mixture being set at? Secondly, you may have actually got ice But usually that will clear.
No, but this happens all the time, Jim. So
All right. It sounds like the mixture's not set. But Rob, do you have any thoughts on that?
I mean, I would, yeah. The mixture on there's not a great deal you can do with them. I mean, the mixture on carburetor engines is basically idle pretty much only. And what it sounds like there is potentially I would definitely have the carburetor looked at. The float height could be too high, which is giving you an extra rich mixture. So, you know, if you know someone that's got carburetor that you can swap over to troubleshoot it, that would be definitely the first port of call. If failing that, I would definitely have the float level in the carburetor checked.
okay, thank you.
But by the way, Eleanor, don't not use carby, even though if it is running rough.
No.
Yes, that was my next kind of half question, as in I always do, because that's what we've always been taught, regardless of the type of airplane. Well, obviously some you don't need to. Okay, understood. But we flew it all the way to Romania, to be around Europe, to Macedonia. We were planning to fly to Morocco as part of the PPL IR trip, as you all know, but unfortunately we had to cancel that. So maybe we need to look into it again. So it's always been like that. It's not something new, but I wanted to understand a bit more. Thank you very much.
All right. Okay. Anybody else? Good. All right.
I think just to conclude then, Jim, yeah, thank you for doing that. David and others have commented that you're obviously extremely knowledgeable, and thank you for Rob and colleagues for supporting you in answering those questions. So this video is recorded and it'll be available in the next few days. If you think of any other questions, please email them in either Jim direct or to myself at events. And we are just finalising details for the annual conference in the summer. So hopefully we'll have a physical get together soon, which would be very good.
Yeah. Can I just noticed something from Ian Roswell. Oh, it's to me directly. Okay.
Yeah.
Right. So Ian, yes, I'm very happy to fly with you if you want. So let me know. The other thing is, if anybody wants to do any of this in more detail, any of the leader peak stuff or engine monitor stuff, then I'm very happy to spend time doing that again. So we'll just let Craig, just email Craig or indicate to Craig that they would like to do that.
Great. Thank
okay.
you. Thank you all for staying, and these extra 15 minutes as well. Appreciate all of your time. Jimmy, you're okay to stop the recording, and yeah, we'll make that available very soon. Okay. Thank you all. Have a good evening.
Thank you. Thank you very much, Rob. Thank you, Graham.
Thank you. Thanks.
Thank you.
Right, Graham.
Take care.